awesome project we did in the summer. We went to Nicaragua to produce this black stuff that we know as biochar. So a brief introduction on what is fast pyrolysis, how we produce this biochar. So basically we took biomass, that is a material, organic material rich in carbon. We process it in heat and in absence of oxygen, and then we get a mixture of gaseous, liquid, and solid products. That's basically what we do. And this is the face of our major professor, Dr. Brown, you might know. And what we do in the Bioeconomics Institute basically is optimizing the production of oil. In this case, in the project we went to Nicaragua, we wanted to optimize the production of this biochar, the solid product. Okay. So what we did, basically our experimental approach, we went there, we found whatever material they had there, whatever facilities and tools to lower the cost of production. We found the biomass, in this case rice husk. We built the reactor, produced the biochar, and then we did some plots. We applied some biochar, manure, and mixture of both in some plots to later measure the greenhouse emissions. And we worked there with this organization called Emerging Opportunities for Sustainability. This is an organization that was born here in Iowa. It's run by ISU alumni, and they also have an office back there in Nicaragua, and they produce all this cool stuff like chlorination devices, cooking ovens. They have irrigation systems, and they have been impacting, with this small group of 10, 12 people, they have been impacting like 30,000 people there, giving them new opportunities for a better quality of living. And this project was funded by this European organization called FLIC. So this is the people from EOS there in Nicaragua. You can see these are some of the products they have. These very cheap ovens, very efficient. They produce bread, and they do start businesses with this. They also have the chlorination devices. They have biodigesters to produce gas to cook with those gases there, and instead of using the wood. We went. Sorry about the location of the star is moved. So we went from Iowa all the way to Nicaragua. We were in this very small city called San Isidro. It's mainly an agricultural city, and they had this huge production of rice husk. So what they do with this rice husk right now? Nothing, basically. They sometimes take it and sell it as a feed for animals. But it's a very small amount that gets sold that way. So we took the rice husk. This is a very nice, thin, uniform, dry biomass source, and we produce the biochar. So to continue our presentation, Matt Kiefer. Sorry. So this is the cool part. So the numbers. This small agricultural site, they have this potential of production of biochar. It's like 1,000 tons of biochar that we can produce, and imagine the impact we can have there in solar amendment applications there. So now, Matt.
So now we move on to the construction of the reactor. And needless to say, building this reactor is a little bit different than we would have done in our lab here at Iowa State. We literally searched the entire country of Nicaragua for materials that we utilized in this project. We dug through like garbage yards, we went through people's houses, we stopped at farms on the side of the highway to pick up materials, literally using anything we could to keep our costs low and keep it using local materials. Here are some of the EOS members that were helping us build the reactor. Here we're putting insulation on the reactor. At the end of our trip, we actually had run and made all of our biochar. We designed a second reactor so that we could hopefully optimize it, make it more efficient. We put pressure gauges, temperature gauges on this reactor, made it a little bit smaller, more compact, and hopefully it would have a higher throughput. Okay, so here are pictures of us producing our biochar. At first we were a little bit worried because the first test we ran, we put biomass into our reactor, heated it up, we processed it for about 45 minutes, we were taking out our biochar, and what did we have? Unprocessed rice husks. We had no biochar our first time, but we contribute that to possibly some moisture being inside the reactor before we started. So after we got it going, we started producing some biochar. In the middle here, you see our quench system. Very simple. It's just a bucket of water. We have a picture of inside of our reactor. We have a couple of the trials running. Now, in these pictures, when you see the flame coming out the back end, that's all energy that's not being utilized. So our system was not as efficient as we want it to be, and we're going to be working on that to continue to improve the efficiency. Here is a picture of us after we had made our biochar. We produced this biochar in about 2.5, 3 days with this reactor. I think we processed about 120 kilograms of biomass and turned it into about 50 kilograms of biochar. A few things about the efficiency of our process. With slow pyrolysis, we usually get about 30–40% of the biochar yield. And that is what we, in fact, got when we processed it. That means, however, that 36% around there, about a third of the energy in the biomass is retained in the biochar, but the other 65%, 64% is wasted in heat, gases, and other things. So how can we make our system more efficient? We're going to utilize that excess energy in preheating our biomass, evaporating off some of the moisture. We also use propane to fuel our reactor. And we have the energy balance in our reactor of energy in to energy out is 1:2 fossil energy in, which is not a very good ratio. We are going to be working on reducing that one greatly in our next models. So talking again about the process efficiency, you can see that 2/3 of our energy in our process was literally wasted. It was just blown out the back of the reactor. So we need to find ways to utilize that excess energy. Also, with being a batch process, there was a lot of time spent warming up the system. About 30 to 45 minutes each time we turned on the system was spent just heating up the reactor itself. And then it takes about 45 minutes to process a batch of biomass. So there's a lot of time and energy spent in this heating up the process after we had taken a break or we came back the next day. So there are many ways to improve it with a continuous system. There, obviously, with the insulation, drying of the biomass, being able to put more biomass through our system, improving our combustion efficiency with oxygen flow, and utilizing all the energy of the system. There are many opportunities to improve. We also have a video of our reactor running, so you can get an idea of how much energy is being wasted. Oh, shoot.
That's right.
As you can see, there's a lot of fuel coming out the other end. A lot of wasted energy.
And this is only the syngas being, well, we like to call it non-condensable gases, but they are flammable gases. Okay, there's hydrogen, carbon monoxide, there's methane, there are small hydrocarbons as well. So all those are all this energy that we're utilizing for combustion. So once the pyrolysis kicks in, all these gases are more than enough than what we need for the processing of the biochar. Okay, so the propane that we utilize here is mostly to start up the reactor. But if we find a way to make it continuously, well, the energy is substantially reduced.
So we did some preliminary cost data on our system, and on the left side you see our batch system. On the right side we estimated a continuous system. So for a batch system we spent about $145 on the materials. Major costs for our batch system are the labor and the fuel that went into the system. However, when we look to a continuous system, you can see much higher capital costs, much higher operating costs, However, the feedstock and the capital are the main cost contributions in the continuous system. You can see here when we have our batch reactor, we only have a lifetime of about 2 months. That's because it's literally a 55-gallon drum. When we automate our system and we turn it into a continuous, and we have a lifetime of over 5 years to distribute our capital costs, we go from the cost of biochar, 63 cents per kilogram with our batch system, to 8 cents per kilogram with a continuous system, or $80 per ton. So there's a lot of room for improvement from our batch system. We just are showing that it's feasible. So after we produce our biochar, we had to mix it with our manure to get ready for our plots. And what we did is we utilized digested manure. This is taken from the biodigesters of the nonprofit group we worked with. We did some sample preparations, we did some moisture calculations, mixed up all of our samples, and put it in plastic bags so they're ready to go for the field plots.
All right. Well, good afternoon, everyone. Before I jump into the greenhouse gas measurement, I would like to tell why it's so important to measure greenhouse gases. Okay. So today, everything that we do is related with fossil fuels. Okay. When we drive our car, that 20 gallons that we have in our tank is combusted and turning to CO2 and water. Okay. We increase the temperature of our houses, we start burning more natural gases. The same when we use electrical appliances. It's more fossil fuel, more coal being utilized to produce that energy. And the problem is, it's not renewable. And the biggest problem is the amount that we're using. We're producing a huge amount of CO2 that we're building up into the atmosphere. Before the Industrial Revolution, we have 280 parts per million. Okay, it's very little amount. Okay, but very little increase has very pronounced effects in the ecosystems around the world. So now we're around 400 parts per million. Okay, we just break the 400 a few days ago, a month ago. So this is building up, and there's nothing actually to reduce that CO2 emissions. We're utilizing agriculture very intensively, and we're producing more CO2. So there are lots of organizations and lots of people trying to think how we can recapture this CO2. And we're saying, well, biochar can do a great deal of that. It won't do a lot. I mean, a lot of what we're doing, but it will do significantly amount in a way that is being utilized for other things. If we improve the quality of the soils, then we're sequestering carbon while improving the agricultural yields and so forth. So measuring greenhouse gases, it's very important. There's a lot of questions around how we measure it, and if we're doing a good job of measuring. And the purpose of this study is going there and saying, you know what, we can sequester. It's very difficult to calculate exactly how much you sequester, because anything you do in the soil, you might be incrementing the CO2 emissions. So in this one, just to be safe, what we did was going there and putting a lot of biochar, a lot of carbon being in a recalcitrant form in the soil. So we measure the fluxes of the CO2 being produced from the soil, and that's what we subtract to the carbon sink that we're putting on the first step. Make sense? Hopefully. Anyway, so these are the plots. For example, we chose 3 farms. One is a prairie. Over there is a prairie, just the animal go back and forth. And this is a soy plantation, and this is an orchard, a citrus orchard. Okay, this is a citrus orchard, for example. And here you see, this is the biochar, this is the control plots, this is the manure. It's not really manure, it's digested manure. Okay, so it's a little quite different in terms of methane emission and some other, and nitrous oxide and so forth. And that one is the mixture of both. Okay. So basically, okay, what we're doing is we go there and we put these little chambers and we measure the flux, the concentration increases in these chambers. Okay. We measure 3 gases that are the most important in agricultural emissions: CO2, methane, and nitrous oxide. Okay. So most of the fluxes are CO2, but careful, because nitrous oxide, for example, if you get a little bit of nitrous oxide production, the greenhouse warming potential of this gas is 300 times more than CO2. So a couple of percent parts per million here makes a huge impact in the overall greenhouse gas portfolio of gases. Okay, so basically, here the pasture produces the most, and careful because this is only production. I'll explain a little bit the other system, all the ins and outs. The orchard burned half of the pastures, and the beans 25 tons. And this is 25 parts per million per minute. Methane, very little. Actually, we might have some oxidation of that methane. Okay, so reduction of the methane in the air through the soils, and a little bit of nitrous oxide, but it's not that much. If we put them all together in the same basis, if we account how much CO2 equivalent we're producing from all these scenarios, this is pretty much how it looks. Pasture 46, 12, and 24. So if we account how much carbon we're putting in our biochar or in the manure, and we translate into the same currency in CO2 equivalent, we're putting 50 tons of CO2 per hectare, 3 and 54 both of them. Okay, and here, let me show you. This is what we're looking into. So if we say, well, the treatment of manure we're producing 32 tons of CO2 annually, and this is, again, we have to be very careful. We study 8 weeks, okay? But most of the fluxes in all these gases are when you do it, when you start, all right? So that's why we're pretty confident. We think we have a pretty decent data. So from this 32, it's only 8 tons more than the control, okay? And from this biochar manure is 6 more than the control. And in this one, for example, we're putting 54 tons of CO2 equivalent. And we have to be very careful because this is it's just a snapshot. If you increase the production of vegetables, for example, with the biochar, that's what we are intending to, you're sequestering a lot more carbon in the biomass itself than what you probably are putting there, okay? So these are very rough numbers. And then you go and say, well, but look at the pasture, we should plant everything soy, okay, produce the least. But it's actually, we're only measuring the outs. The pasture is putting a lot of organic matter into the soil by its roots, by its vegetation decay, and so forth. So it's obviously we'll have more production, but also have more inputs. And we're only measuring outputs, okay? Just a rough cut. The idea of all this project was we can sequester carbon in a very simple way, and we can actually improve the agricultural performance of those soils, all right? And well, now we're moving on, and we're trying to make this bigger, and we invite anyone who is would like to collaborate with us. We're writing some proposals and start applying for bigger amount of money. Okay, so we can do this with the non-profit over there, and there's another non-profit is Canadian that are looking into carbon sequestration only. So we'll partner with them to develop bigger projects. All right. So that's pretty much the summary of all this. Our hope, well, is from here account CO2. We know that we can account them. The problem that we need to resolve is, well, we need to figure out how much are the sources of error, okay? Even in the GC measurements, we got some error. And we're saying, you know what, you're producing this many parts per million per minute, and maybe your error is within that range. So we're gonna run some statistical analysis and see whether this is statistically significant, whether we're really sequestering that much carbon, or we can measure, we know that we're sequestering, but can you measure that much carbon you're putting in? The fluxes and the variation, the fluxes within day are significant. So we're going to put all this into this model and figure it out afterwards. But again, one invitation or suggestion that we have is, you know what, you got some ideas. Out there are lots of funding, all right? So if you're interested in any project you would like, just, find out a student, partner up, and apply for funding. There's money out there, and you guys can do lots of other things beside our research. Okay? We're pretty busy with research, but all these things are really good. I don't know, professionally really good. Okay, and we, understood so much more of the biochar process, of the chemical process. We go to BCRF and we see all these huge reactors. Say, well, that's great, but we can do something a lot smaller and a lot more simple. We get something, and that's our hope with this project. So, with that, I will conclude this, and if you have any questions, we'll be glad to answer.
Are there any questions for these three?
How did you get feedstock cost? The feedstock cost?
Feedstock cost was 0 because we were literally taking a waste product. However, when we moved up to the continuous scale, $10 per ton, we estimated that we would have some cost associated with it. If we were removing a lot, they were likely to charge us some, but there was no feedstock cost initially.
So they're looking ways to remove that. Actually, they're burning it, okay? So it's an easy way, that we can utilize this into a valuable product. So they're burning it, or they're leaving it to the field, and then they have more extensive tillage and so forth, because there's quite a bit of biomass they need to get rid of before they plant it. So it's a problem.
tell for the 5 years.
Again?
5 years?
Yeah, I
That's-
think it's 2.
That's an assumption. Those are two assumptions that we put in the model. It's just an estimate.
Yeah. If we're gonna do this in a bigger reactor, well, we're gonna do it real. So we put in real money and real time.
Okay. Another question is, you mentioned that a large amount of energy was waste because of combustion. Why do you add a heat exchanger? Then the energy produced in the combustion process can give the energy to the biochar production.
Yeah, absolutely. Our budget for the reactor was a couple $100. So, and then actually we have 3 weeks to construct the biochar, and then we have a total amount of 3 + 8 weeks of measuring and project in total. So it's not that much. So when we went there, we're literally screw the efficiency. We need this much biochar for our research, and we try to make it.
But in our second reactor, those are some ideas that we're gonna implement